Well, hello, everyone. My name is John Berger. I'm an AVP in technology with LexisNexis Risk Solutions. I'm going to talk a little bit today about how we at Risk Solutions started leveraging the HPCC software when it became available, and how we started testing that on Azure Cloud specifically. So the date started back on March 31st, earlier this year. This is when the HPCC platform 8.0 release went gold. And that's where our fun began as a company. And we had quite a bit ahead of us in terms of being able to migrate our existing HPCC infrastructure at risk into the cloud. Put a little bit of that into perspective. Just within the one data center inside of Boca Raton, which was the initial target of the migration, we had very close to 16 petabytes of storage on HPCC, well over 30 terabits per second of network bandwidth that we have to account for, 56,000 CPU cores within our HPCC infrastructure, and over 300 terabytes of RAM. Within the infrastructure. But that's not all, because that's just the environments that actually are processing the big data. In addition to that, we have backup for all the data that is too valuable to lose. That's about a little bit over 4 petabytes of data that we've got inside that environment. 1,464 CPU cores, close to 3 terabytes of RAM, and about 3 terabits of network just used for the backup of that data that I talked about earlier. So it's quite a bit of storage, compute, processing, and RAM compromised in several dozen HPCC environments or clusters. But with all that in front of us, we didn't want to stop there. And so they implemented the Alpharetta business case, which was really about another one of our business units called for insurance, where they also wanted to migrate their HPCC resources. So you can basically take all of the numbers that I talked about on the last 2 pages and multiply them by just about 2. The number is about 1.8, but effectively it's about twice as much in terms of storage and compute and network resources. So needless to say, we had quite a feat in front of us, and we needed to make sure, because it is such a critical piece of all of LexisNexis risk products. It underpins all of our products. And it's very, very important that we get it right. And we make sure that all of our data engineers and data scientists are going to get and be able to use systems in the cloud at the same type of performance, and ideally pick up the benefits of the cloud while not losing a lot in terms of performance. So it's quite the challenge, and we had to get started early. So where do you start with something like that? That's really the question here. This is an enormous effort. It's 20 years of growth that happened within our data centers, and just finding the place to start can be a little difficult. And you may find this within your own organization as well, although your scale may not be as large. Obviously, you start somewhere. And my recommendation to you for this would be that you really start at the basics, and you start with the basic building block of a process. And in Thor, as an example, this would be the worker process of the Thor node. And start to say, what is the requirements that worker process needs? Again, for Roxy, if you're targeting Roxy, it's the same thing. What does that Roxy process need in terms of resources? Luckily for us, we had a very good understanding of what we've always targeted for in our benchmarking and when we're building new services. And it basically boils down to these features. Really, about per process, we want 2 CPU cores. We want about 12 gigs of RAM per process, about 1 gigabit per second of network, and about 250 megabytes of read and write bandwidth to that process. Well, as we started to map processes into Kubernetes, processes really start to become containers. A container really holds one main process. That's the pattern for containers. And so ultimately, these resources really started to become of what resources do we need per container? And that's why you see them represented as boxes on this thing. So you can think of these resource needs as what resources do we need per container. And ultimately, you need to decide how many containers are going to be running in order to make your workload work. So the next step in this is, okay, we know how big our containers are, but ultimately there's a lot of virtual machines out there. Depending on your cloud provider, you could have upwards of 200 virtual machines. And so each one of these virtual machines has slightly different ratios of CPU and memory and RAM and storage capacity. And so as you start to stack these containers on top of them, you start to realize that once you fill up one area, maybe it's width or the height or the depth of that particular vessel or that virtual machine, you start to have extra resources that ultimately you're paying for because you're renting these VMs, by the hour. But the containers may not always fit perfectly. So it's really about matching the ratios that are on this container to the appropriate virtual machine. And like I said, there's over 200 types of these virtual machines, and you have to go through each one individually and take a look to find out how these containers might map against those virtual machines. So the first step in this process of going through those types is really just doing the basic math. Or, in areas where you might have a bunch of GPUs or something like that you're not going to leverage, you can eliminate those pretty quickly without doing any kind of testing. And you start to find that you can eliminate somewhere around about half of the virtual machine types just by looking at them and doing an initial assessment. After that, it really starts to become benchmarking. So what do we mean when we talk about benchmarking? Well, the cloud vendors, they've come out and they've said, we expect that this virtual machine has a certain number of resources. It has this much network or CPU or RAM. And ultimately that's great, but really you want to test those performance. So you take benchmarking tools, there's a lot of them out there. I mean, you can go and grab one from any kind of open source Linux repository, CPU bench, IOStat, and among others, FIO. As an example, for network testing, we use iPerf in a lot of cases. So, and we start to benchmark and make sure that each one of these VMs or these vessels where our containers are going to run actually meet the specs of what the cloud vendor said that they would meet. And ultimately, you get to a point where you start to eliminate some. Either they can't meet it because they don't have the right specs, maybe they're over-spec'd and you wind up, once you've used up all the CPU, you have all this extra storage bandwidth, or you have all this extra network bandwidth that you're not going to be able to use as part of your system, and therefore it becomes a cost elimination point. But ultimately, you start to eliminate a number of these VMs that get it down to a fairly small and reasonable set of potential targets. And then you move on to the next phase, which is really benchmarking these VMs in parallel, because ultimately in most cases, you're going to run clusters that span multiple VMs, potentially upwards of 400, 500 different VMs. How well do those VMs work in parallel with each other? Because while a VM can have individual performance that's very good, sometimes the cloud vendors take a few they make a few decisions in the way that they do things to oversubscribe certain pieces of their network, as an example, where they don't expect every one of these VMs to be talking on the network at exactly the same time. But as you and I know, in parallel systems, that is the case. We're going to make 400 of these VMs talk on the network at exactly the same time. We're going to make 400 of these VMs talk to their storage backend at exactly the same time. How does that play within their system? Do they have bottlenecks outside of the VM space within their system that could affect what happens when you put a bunch of these machines together? So you start to benchmark these things in parallel, run a lot of iPerfs one against each other 400 ways, run CPU benchmarks 400 in parallel. Run storage pieces where you're attaching and doing FIO against the storage, measuring the performance in parallel on the number of VMs that you intend to target as part of your cluster. And in that process, you start to eliminate things based on what what you find in this argument. And I can tell you, this is one of the areas that you probably find the most. I actually represented the elimination here in Wildfire. That's why it's green. So if you choose to eliminate them in Cersei Lannister style, that's up to you. But ultimately, you're going to be able to eliminate a number of these VM types just based on what's happening on the overall system when you run them in parallel. So after that, you start to form some opinions. You've now looked at the containers, you know what size container you're working off of. And I would encourage you that if you do not know the container specs that you want to target, leverage ours. They're published out there on the HPCC Systems website. You have the ability to go out there and look to see what those specs are. If not, these presentations will be available to you, but just use ours to start off with until you start to determine what your own container specs need to be for what you're going to target. And then ultimately, you're going to start to figure out what VM sizes and which VMs are potential targets for you to use for different types of your work, different types of workloads, and for your end users. After that, you're going to want to start to increase the complexity of your test. It's fine to start with some basic benchmarking tests. These will involve, normal benchmarking tools, as I mentioned earlier. But as you increase the amount of testing that you're doing, you start and you get test by test and you make your way through those tests, you increase the complexity at every stage. So after you've done basic benchmarking tests, you start to work towards basic HPCC tests. That may just be as simple as running a single query against all of your different query types, or it could be as simple as running benchmarking tests within the data space itself. We commonly use TerraSort test for these types of purposes, where we can generate a terabyte of random data, and then we go and sort that terabyte of random data, and we're essentially timing how long that it takes. The reason that we do that is because it stresses a number of different subsystems within the HPCC. The first one being storage, to be able to read that terabyte of random data off of whatever your permanent storage is and read that up into RAM. It then tests a local sort, which is essentially going and doing a RAM to CPU test between RAM and the CPU resources, doing the local sort. Then it starts to do what's called a global sort, in which case you're using network bandwidth at full bandwidth. All the nodes are talking to all of the other nodes. And using full network bandwidth during that test. Then it does another local sort, which is CPU to RAM, and then ultimately your final write, which goes down to the drives and test your write speed. And so you're moving up the complexity. Now we're using a benchmarking test that's being done in parallel using the HPCC software. And then once we get beyond those tests, you start moving into real world, real data, real solutions test. That moves into our developer space, into our data engineering space, where they start to move through different workflows, different sorts of things, just going beyond just a simple sort. They start to do linking and fuzzy matching and a number of other things that we do and expect to do on a daily basis. And as that complexity move up, you're getting more and more confident that the solution that you've got in place works. And if you do discover something at the later stages, it's easier to ultimately troubleshoot because you have all of that base of data, all those base metrics that you've been working on the entire time as you go through it. So increase your complexity as you go up. The next thing is it's very important to identify your outliers in the process of doing this. This is just a quick example of a Roxy graph from one of our earlier tests where we're going against individual queries. And you can see we're testing 673 different queries and comparison of performance between on-prem, or not on-prem, but a bare metal system with the same data, same queries versus an Azure system where it's containerized and running on VMs. And you can see the areas that are highlighted in kind of a light pink gray area. Those are areas that we identified as major outlier points that we had to go in and investigate to find out what they are. In this particular case, it ended up being that these particular queries made calls to a system back on-prem that we didn't realize were part of the test. And so what you're seeing is additional latency that happens between going from, the Azure ecosystem back across the lines into our main data centers. And so that's what accounts for these particular things. But these outliers can happen in all kinds of different areas. One of the areas that we found out about, I'll give you a couple of examples, is they have network flow limits, as an example, within Azure, where only a certain number of network connections can be made between other nodes before they start to get throttled. That was something that we discovered early on. In addition to that, we found packet loss in certain VM types that was causing problems with Roxy, upwards of 1% packet loss. That ended up turning into a problem between the AMD processor and the Microsoft hypervisor, that Microsoft had to go back to their drawing board and ultimately work with AMD to replace those machine types as a long-term fix. In addition to that, you find other things that we can overcome ourselves within our own platform. One example of that is we're really targeting blob storage as one of our potential storage mechanisms. Blob storage relies on an object store where the data gets randomly sharded and written across the object store itself. That object store is, it wants a certain amount of randomization in the names when you create file names. So ultimately, those file names, we had to randomize a little bit more the way the file names were created in order to increase the performance against the object storage itself. So you'll find these outliers multiple places within the system, and just identify what they are. You have to take your time and investigate what the potential cause of them can be. And ultimately you get wiser, you get better at being able to troubleshoot the system. You find optimizations in how the platform works against a certain cloud provider, and ultimately make it better. And the other thing that I would add to this is begin to experiment. This is an opportunity for you to try different things, try different machine types, try different ideas about how you might be able to modify configuration settings within the HPCC in order to optimize a system. So don't just limit yourself to testing what you've already known, but also be able to reach out. The cloud gives you the ability to test fast, fail often. Take advantage of that because you may find that there's different ways and different ways that you can essentially run these systems in order to benefit you either financially or from a performance standpoint. So definitely experiment as you go through things. And then you're going to start to form, as a combination of these, more opinions about how things should work and where your best optimization is across a certain ecosystem. And so as you start to form these opinions, it's very important to settle in on them, make sure that you've got good reasons for each one of them. And then you want to start to record those opinions in code. And really, this is where it's very, very important that you don't just take the basic Terraform module. Gaji did a great job of putting out an open source HPCC Terraform module, and we also use that as our base. We also have produced an Azure Kubernetes service Terraform module. We're the owners of that. We've produced that open source as well. Those two things can be combined together to form an HPCC, but ultimately it's these custom opinions that are found by this experimentation that need to be baked into code. And ultimately you get this wonderful pink muffin at the end of it. Looks really appetizing, but ultimately what you're baking in there is you're baking in all of this work, these months long of testing, benchmarking, experimenting, to ultimately bake in an opinionated way of creating an HPCC for your particular workload. Ultimately, to empower those data engineers so that we can take that HPCC opinionated module, a module that really belongs to the risk solution group in themselves. We give that to our data engineers, and using that module or that library, they can create the optimum HPCC environment for their particular workload that runs their containers, that does it in a cost-efficient way, that meets their performance numbers, and ultimately makes it very easy for our data engineers to be dynamic and agile in the way that they work. So with that, I'll leave it for questions. I appreciate your time today, and thank you very much.